Can you hear us?
I can hear you. Can you hear me?
Yes.
Eleni, can you hear me?
Hi. Is anyone presenting live? Do you know? Everything?
Live, yes.
Yes. Do you have the presentation slides
Yes.
so I can load them? We're gonna need that. This is not working. Yes.
Eleni, can you hear me?
This is not working. Sorry. Just give me a second, please.
Avete le presentazioni da consegnare? Sono due italiane, quindi
Can I copy live
ho visto un microfono.
to check?
Buono.
Arianna?
No.
Hi. We are copying the presentations and we're gonna. Okay. Okay. Is this one? Okay. So you can hear us, right? We're ready to start. I think.
Prof? Senta, mi sentite attraverso il computer?
Sì, adesso sì.
Ok. Perfetto.
Sì, sentiamo, o almeno. Lei conferma che Giulio sei tu, giusto?
Sì, un attimo. Sì, Nicoletta, ora ti sento e stavo verificando che sentissero anche nella stanza.
Ok.
Ok. Federica Pes, la vedo collegata?
Sì, ci sono.
Ok, grazie. Sì? Sì.
È in linea?
Sì. Ok.
Good afternoon to everybody, and we just start with the first presentation that is about a mathematical model for the analysis of the iPhone image in healthy and diabetic patient by Arianna Cavalier.
Okay. Search now. Okay. Okay. So no. So okay. Okay. And full screen. Presentation. Thank you. We can start. And hide. And hide.
Okay. Good afternoon. It is a pleasure for me to be here. In this talk, I will speak about some recent results achieved together with my supervisor, Professor Gianluca Vinti, which deal with the application of the sampling Kantorovich operator to the study of high fundus images of healthy and diabetic patients. So in order to set the medical frame where we work, it is necessary to recall some basic notion about the structure of the human eye. In particular, we are dealing with the retinal part of the eye, which converts light into electrical signals. We are dealing with these two images, which are acquired with the optical coherence tomography, which is a new technique that I will describe in the next slide. In the left part of this screen, we can see the superficial capillary plexus, which is the superficial part of the retina, while on the right part, there is the choriocapillary tissue, which is the profundus one. So every time we acquire an image of the retinal part of the eye, we have these two images, which are rigidly connected. So the optical coherence tomography is a relatively new technique, which is non-invasive because does not require the injection of the contrast medium, unlike the fluorescent angiography, which is, however, the gold standard diagnostic procedure to detect retinal pathologies. The optical coherence tomography works by emitting a low-power laser beam, which split into parts. The first one is directed towards the eye, and the other one is reflected toward the reference mirror. Then these two waves are recombined together to create an interference pattern. What are the main features of this technique? First of all, it's non-invasivity. Then it is a fast technique because it is able to acquire multiple scans of the retinal part of the eye, so 4 or 5 or 6 images in few seconds. And then, however, it is it have a lower quality of image if compared with the fluorescent angiography, because it is affected, these images are affected by noise produced by the scan of the OCT and also by the eye movements, because the eye is an organ which is constantly moving and deforming. So our objectives are to apply a series of digital image processing technique and also the application of the sampling Kantorovich operator that I will describe later in order to improve the quality of these images. And also to evaluate from a clinical point of view how the incidence of the diabetes on these images. So the principal steps are a registration in order to overlap these images, an averaging process in order to reduce noise, then the application of the sampling Kantorovich algorithm, which plays a crucial role, and then a cluster counting analysis, which consists in counting the connected components of the image, and in order to do this, we need to threshold these images. So in order to set the mathematical frame where we work, it is necessary to recall the sampling Kantorovich operator, which I recall in its multidimensional version because we use it to reconstruct digital images, which are bidimensional signals. So they are defined by means of this series, where the function f is a local integrable function such that this series is convergent. Inside the brackets, we have an integral mean, which from an applicative point of view is important because it allows to reduce the time jitter error, which is an error that occurs when we are not capable to capture exactly the information in a point, but this process is affected by a perturbation. So doing a mean allows to reduce this error. And if you think about it, this is what happens when of almost all the image acquisition system, which does not capture exactly the information in a point, but always do a mean. And the function key is the kernel of the operator, which is a function which has to satisfy some suitable assumption. Indeed, we require that the kernel key belongs to L1 and is bounded in a neighborhood of the origin, then that the so-called singularity assumption holds, and that there exists beta such that the so-called discrete absolute moments of order beta are finite. While the sequence TK is a sequence of real numbers, not necessarily uniformly spaced, with some boundedness property from below to above. It is necessary to point out that these assumptions on the kernel functions are not restricted because are satisfied by almost all the kernels known in literature, and then I will show you some examples of them. And under these assumptions on the kernel function, these two fundamental results also, which are fundamental also from an applicative point of view because the two ones which allow us to reconstruct digital images. Indeed, if the function f is a continuous and bounded function, then the family of the sampling Kantorovich operator reconstruct the function f when the parameter w of the operator increases, whose reconstruction holds uniformly if the function f is uniformly continuous and bounded. An analogous result also if the function f belongs to LP. So what about some kernels which satisfy the previous assumptions? For example, we could consider the Jackson-type kernels, which are tensor product kernels, which can be constructed by the product of one-dimensional kernels of the same type. These are band-limited kernels with a fast decay. But we can also consider kernels which are not of the product type, such as the Wendland kernels, which are radius kernels, which can be defined in a recursive way by firstly considering the positive part of this function. And these are compactly supported radial basis function. And there are also other kernels, such as the Fayet's kernels, the B-spline kernels, and so on. So how this theory could be applied to the problem of the reconstruction of digital images? Well, by firstly considering that an image is a matrix of numbers where each number corresponds to a gray level. So for 8-bit coded images, we have 2 to the power of 8 gray levels, ranging from 0, which corresponds to black, to 255, which corresponds to white. So given a matrix, we can construct the so-called image function, which associates to each point inside the pixel the constant value aij. This function is fundamental from an applicative point of view because it plays exactly the role which plays the function f inside the sampling Kantorovich operator. So it is exactly I, the signal f that we consider. So we can numerically compute the sampling Kantorovich algorithm by choosing one of the kernels known in literature that I previously mentioned. So this is an example. If we consider these superficial capillary plexus images, these are two reconstructions made by using the sampling Kantorovich algorithm with the Jackson-type kernel, with the parameter k of the kernel equal to 12. On the left, when the parameter w of the operator is equal to 10. On the right, when the parameter w of the operator is equal to 30. And as you can see visually, by increasing the parameter w of the operator, we get an always better reconstruction. And this is in accordance with the theoretical reconstruction results. So if we increase the parameter w, the family of sampling Kantorovich operator reconstruct the function I in this case, which is this one. So this scheme summarizes what we have done. So we have at disposal both superficial capillary plexus images and choriocapillary tissue images from 20 healthy patients and 16 diabetic patients. It is necessary to point out that diabetes does not mean that these patients are eye diseased, but are more prone to develop eye disease. So the first step is to register those images by choosing a target one. Then I will explain how this target is chosen. So we do first an affine registration followed by an elastic one. Then we average them in order to reduce noise and reconstruct them with the sampling Kantorovich algorithm. This step is important because the sampling Kantorovich algorithm has a double behavior because it acts simultaneously as a low-pass filter, thus reducing noise, which is contained in high frequencies, and also as a rescaling algorithm. So we can double inside the original image and hence have an high information content, which is important from an applicative, from a clinical point of view because it allows to visualize better the clinical structure of the eye. And then, in order to assess a cluster counting analysis, we threshold these two images by using the well-known techniques of Panzarkar and Otsu in order to count the connected components. Why the registration is important? Well, because if we do not register those images, we obtain this blurred effect. So it is necessary to overlap exactly the structure of these images. So we firstly assess an affine registration. And this is the result on one image by doing this first affine registration. How the target is chosen by, in a visual way, by choosing the less noisy. So a mere affine registration is not sufficient if we consider that the eye is an organ which is constantly moving and deforming. So also an elastic one is needed, which is done by exploiting an algorithm which is called Bianguard-Jays, which uses B-spline functions. And this is the results when both the registration processes are done. Then we average these images, in order to reduce noise. And then we reconstruct them with the sampling Kantorovich algorithm. So we obtain an image which is less noisy and also doubled in size, so which has an increasing of the information content of both superficial capillary plexus images and also the choriocapillary tissue ones. So how we have evaluated these results? Well, we want to evaluate also the incidence of the diabetes on these images. So we want to evaluate the connectivity of the capillaries. You have to know that from a literature point of view, medical literature, the retinal tree is thought to be fully connected. So ideally, it is composed by one single path. So we want to count the connected components of these images and see when we have a lower number of clusters, lower number of connected components, because it is more consistent with reality. In order to do this, we need to binarize these images. This is what happens if we binarize the superficial capillary plexus images with the well-known techniques of Pansalkar and Otsu. On the left, you can see the binarization with the Pansalkar method, which tend to overconnect vessels. So we have an overconnection of the capillaries. On the other way, if we consider the Otsu method, we have these artifacts in the macula. So in order to overcome these issues, we have exploited a technique which is based basically on a logical end operator, which uses the Pansalkar method in the region of the macula and the Otsu method outside the macula. So it is a mix of these two methods, an hybrid threshold techniques. And this is the result after applying it. So it is basically a logical end because it assigns to a pixel the value white if and only if both the two images have the value white at that position. While for the choriocapillary tissue images, we have used the Pansalkar method because it is the most suitable for dealing with images with an non-uniform staining and with low contrast. So we have counted the connected components of these images by using the 8 adjacency principle. And the results for both SCP and NCC image, as I will show to you later, of healthy and diabetic patients, show that if we reconstruct with the sampling Kantorovich operator the averaged image, we obtain a lower number of clusters with respect to the only averaged images, which proves more consistent with the reality. This is also for healthy and for diabetic patients. However, if we consider only diabetic patients, we can see that with respect to the healthy patients, we have a higher number of clusters, which is an expression of the disease, would be a clinical expression of the disease. This also for the choriocapillary tissue images. So we have a reducing of the number of clusters if we apply the sampling Kantorovich operator, both on healthy and diabetic patients. So in order to summarize the results, the sampling Kantorovich operator allows to connect more the capillaries. So we have to have a situation which is more near to reality. Then if we consider the diabetic patients, we have a higher number of clusters, which could be a clinical expression of the disease. Then we have also tried to apply the sampling Kantorovich operator before the averaging process, but this led to similar results. So we have preferred to apply the sampling Kantorovich later because it is less time consuming and also from a computational cost point of view. Thanks for the attention.
Do you have any question?
Okay, I have one question. So you compared the results, the number of clusters for persons which have no disease and diabetic persons that have
Yes.
diabetes. Have you done any study of the evolution of the number of clusters for the same person which has diabetic person? So how this
No.
this disease is
Okay, it's clear.
is changing, and so how these numbers are changing, because it is clear that there is a big difference from the person without any disease and the person which has it. But what is the evolution of these numbers? So are they changing from 2,300 to 3,000 or 2,300? And so it is a way to do that.
Okay, this is an interesting point of view because it is a sort of monitoring the evolution of diabetes, but we haven't done this because this is a study. It is a recent study, so in order to do this, we have to this takes a long of time. Okay, but it is interesting because it gives also information about how diabetes could influence the number of clusters of the retinal tree. Thank you.
Thank you for the talk.
Thank you.
I didn't understand completely when you take the average of different images, what kind of what are you doing the averages on?
The average is pixel by pixel.
Yeah, but
Okay.
the images are representing what different the same image is a different moment for the same.
They are firstly registered,
okay.
and then they are averaged.
Yeah, but the different images what they represent. I mean, it's the same. It's a different patient, different.
For one single patient,
Okay.
we have 6 images of the superficial capillary plexus, for example. So these six images are firstly registered and then averaged.
And the second question.
Yes.
This one. So, could it be meaningful or maybe not to consider a different average for these images? Or no, I'm thinking of maybe there are some images that are, let's say, more common, say that you have some, let's say, outlier images because maybe they're really close to one each other. But if you, for example, have a group of images and you have some images that are slightly more different with the others, maybe if you consider some, I don't know, weighted average between them, could it make sense? Or
In this case, I think not, because we do an average only to reduce noise, because it can be proven that if we do a mean of a certain number of images of the same subject, we reduce noise. And this is important in this case because we have noise produced by the scan of the OCT.
Okay, let's pass it to the
Okay,
next one.
thank you.
The next talk is about improving color image.
Did you see my screen and the presentation? I suppose no.
Not yet.
Not yet. Because I'm not able, I have to share directly the presentation. Okay. Now? Did you see anything? from the presentation?
No, we can just see the browser now.
Only the browser. Because I cannot share all the complete the screen is enabling. So
It's not enabled.
no, they can share the browser, but I cannot share all my desk directly. So I try to do it again.
I'm not sure if it's working, but after clicking on share your screen, you have to click on window, finestra, or full
Schermo
screen.
intero. I try to share all the screen, but it's not allowed to do this. I can just try to share this single screen and sharing the screen, which is the presentation, but it appears that it doesn't appear on your.
Not even a single window, maybe sharing the PowerPoint presentation.
And that's all right. Let us try this. Let us open the PowerPoint directly.
You can hear us, right?
Yeah, I can hear you.
Thank you.
Okay. Did you see now? Or you don't see anything?
No,
Not yet. So now that you have your PowerPoint open, deactivate the sharing and do it again and try. Now it should appear, hopefully.
No, it says that I am not allowed to share my PowerPoint presentation when I try to do this.
Wow.
What browser do you use?
No. And I'm not allowed to share all the screen because I cannot press. Let us do this. No, share that. It fails in sharing. I can send my PDF in a way. I don't know. If this
can you open another browser and log with that browser, perhaps?
Yeah.
Just as a last try.
I can try with Safari and use this.
Because now you're using Chrome.
Yeah, I'm using Chrome.
Okay.
All right, so I'm going to do again the connection. Let us try this.
Just a quick note, when you want to share from Chrome, it will have you the following options. Either a Chrome tab, you will have a pop-up in your screen that says either share a tab or a window or the entire screen. Did you see this pop-up or not?
No, I see it. But it appears.
Okay, if this appears, and you press the entire screen, for example, can you press that?
No, it continues to say that it fails to share.
Okay. Then you try another browser.
I'm trying with another browser. Just
we can change the order for a while.
Yeah.
Before. So,
or the other ways I can send by the chat the PDF but someone there.
In the way, I think.
Nicoletta, if you want, we can have a test in a separate room, so we can let another speaker talk now.
All right. Send me the address and I can test it in another room. And then maybe the following speaker will give his presentation, and then I'll come maybe. All right.
Yeah. So I'll ask Ivan to proceed with the next speaker, and I will send you in the chat the link to the new room, and I will wait you there. So we can.
All right. Thank you.
You're welcome.
Okay, then the next speaker is Federica Pes. The talk is about tracked minimal norm Gauss-Newton method applied to the inversion of FDEM data.
Do you see my screen, my presentation?
Yes, you can start.
Okay, thank you. Thanks to the organizer for inviting me to participate in this workshop. And today I'm going to talk about regularization method in order to solve nonlinear least squares problem. And at the end of this talk, we will see an application in geophysics. So we start by considering a nonlinear function f. We consider a data vector b, and we want to reconstruct a solution vector by minimizing the norm of the residual. In particular, we are interested in solving underdeterminate problem, so a problem in which the solution is not unique. Typically, a nonlinear problem is solved by Newton's method or its variants, such as the Gauss-Newton method. In particular, the Gauss-Newton method is an iterative method in which the step of the iteration is computed by solving this linear least squares problem. And this expression is obtained by a linear approximation of the nonlinear least squares problem of the original nonlinear least squares problem. We prefer to solve damping. We prefer to introduce a damping parameter to ensure convergence of the method. When the solution is not unique, typically the solution is obtained by solving a minimal norm linear least squares problem. So we minimize the norm of the solution S. Or in some situation, the norm of the step S is substituted by the norm of LS. And here, L is the so-called regularization matrix. Typically is a diagonal matrix or up-band matrix. For instance, the matrices reported in this slide, P1 and P2, are approximation of first and second derivative operator respectively. We observe that here we are minimizing the norm of this step and not the norm of the solution X of the nonlinear problem. So in our work in 2020, we studied, we imposed to solve a minimal L norm solution directly to the nonlinear problem. Then, by linearizing the first equation, you obtain the second blue expression, and we solve this problem as a method that we call minimal norm Gauss-Newton method. In this theorem, we prove that the iteration of this method is given by the iteration of the standard Gauss-Newton method, that is when we solve this problem, minus a projection term. Here, P represents an orthogonal projector onto the null space of J. How to find this projector? If the regularization matrix is the identity matrix, so we are minimize only the norm, we use the singular value decomposition of the matrix J. And in this slide, we briefly recall what is the SVD. It's a factorization of this form in which U and V are orthonormal matrices, sigma is a diagonal matrix, and to construct our projector, we need to consider the last n minus r columns of the matrix V. And the projector is given by this product, V2 times V2 transpose. Otherwise, if we have a regularization matrix different from the identity, we need to use the generalized singular value decomposition of a matrix pair J and L. Here we recall what is the GSPD, is a factorization of this form. U and V are orthonormal, sigma J and sigma L are diagonal, and W is a non-singular matrix. To construct our projector, we have to consider the first n minus r columns of the matrix W, and the first n minus r rows of its inverse. Here, R is represents the rank of the matrix J. Unfortunately, the iteration written in this form, the method written in this form doesn't always converge. And the problem is this last term, because this causes the residual to increase and the method to diverge. So a possible solution is to introduce a second relaxation parameter, beta k, in order to control the length of this vector. Now, the question is how to choose these two parameters, alpha k and beta k. A possible simple solution is to consider and only one parameter for both terms, and estimate it by a so-called Armigio-Costain principle. Otherwise, we can use an independent parameter beta k estimate by an algorithm that we detail in 2022 in this paper, and this algorithm considers the residual of the problems, and if during the iteration, if the residual is increasing, then beta is halved. In case of regularization, in case of ill condition problems, we need to apply a regularization method to each step of the iterative method. For example, the truncate SPD, the truncate generalized SPD, or T-con of regularization, and so on. In our approach for the solution of a minimal norm problem, we introduce this truncate method, and the condition matrix J of the system is approximated by its best Rankel approximation, is substituted by its best Rankel approximation in order to obtain a better condition problem. In this slide, I reported the formula of the iteration, in which the matrix L is the identity, and the formula depends on the singular value decomposition, the composition of the matrix J. And here L play the role of the regularization parameter. If the regularization matrix is not the identity, obviously the iteration is written in depends on the generalized singular value decomposition of J and L. And alpha k, beta k are the two relaxation parameters. Now we see the application in geophysics. These electromagnetic induction techniques are used in order to study some properties of the soil in a non-destructive way. For instance, we can
Giulio, cosa è successo?
geophysics is the so-called ground conductivity meter. It's composed of two coils, a transmitter and a receiver. The transmitter creates an electromagnetic field represented by here by the green lines, and the receiver reads the electromagnetic field induced by the soil. By varying some parameters of the device, we can have available multiple measurements. For instance, we can vary the orientation of the coils in vertical or horizontal, or we can vary the height above the ground at which the measurements are taken. We use different frequencies or different distances between the coils. Here we can see the discretization of the problem. The soil has a layer structure, and each layer is characterized by a depth, a thickness, an electrical conductivity, and a magnetic permeability. In this experimentation, we assume to have a constant value for the magnetic permeability, and in our inverse problem, we reconstruct only the electrical conductivity sigma J. This nonlinear model is extensively studied by an interdisciplinary group composed of mathematicians and engineering. In this slide, I reported the nonlinear model is a system of two integral equations. The first one corresponds to the vertical orientation of the coils, and the second one to the horizontal orientation. The model is nonlinear indeed. Our unknown sigma, the electrical conductivity, is inside this function R that in physics is named reflection factor. I don't want to bore you with the details, so we go on. We collect the data in a vector B, the model prediction in the vector M sigma, and the problem of inversion consists of computing the vector sigma by solving this least squares problem. Now, if you think that this guy is walking along a straight line in this horizontal line, we can consider 2D section of the soil, and that is a 2D model. So we denote by sigma j the electrical conductivity of the ith layer in the J dataset, and we collect the data we collect the electrical conductivity in the vector sigma j for each dataset, and in a vector bj the corresponding in dataset. We group all these vectors for each dataset in two matrices. The electrical conductivity is in the matrix S, and the dataset in a matrix B. And we want to solve this 2D least squares problem. In this work, the 2D problem, the problem in two dimensions, is brought to n independent 1D problem. So we to obtain the 2D reconstruction, they obtain solutions, 1D solutions, are placed side by side to obtain that section of the vertical section of the soil. Here we have a first text test example. In the plot of on top left, we have the test model. Here we are assuming that under the ground there is for instance, a metal ball, and there is the change in the electrical conductivity. And in the left part, in bottom, we reported the reconstruction by using the method described in the previously. In the right part, I reported the reconstruction by obtaining standard regularization method. On the top, by regularize the Gauss-Newton method by using the truncate GSVD, on bottom by the Tikhonov regularization. I don't know if you see this horizontal line in this reconstruction. By using standard method, there are some artifacts that there aren't in the reconstruction obtained by our method. These irregularities can be better shown by a plot of the electrical conductivity corresponding to a single dataset, so to a single column. For instance, on the left, I reported the electrical conductivity of the 33rd dataset, and the right, the 48th dataset. You can see that this irregularity does not occur when the solution is computed by the truncate minimal L norm method. In fact, we can compare this with the exact solution. Here we have a last reconstruction, similar to the previous one, but here we assume to have a true holes under the ground, and the reconstruction is better in the case of truncate minimal L norm Gauss-Newton method. Now, what to do now in the future? We can think to reconstruct a 2D section of the soil as an image and not placing side by side the 1D reconstruction. We can try other regularization operators that are used usually in image processing, and in this case, the vertical irregularities, this line, by using these operators, these vertical lines can be avoided. Then finally, since this problem is a large-scale problem, we can fit to solve it by iterative method, for instance, by Krylov methods. And thank you for your attention.
Okay, do you have any questions? So there is no question. Thank you for your presentation, and we try again with
Thank you.
Nicoletta Del Buono.
Yes, I'll try again. It worked. So in the other room. So let us do this. It seems that I'm sharing now. Okay. Did you see now everything?
Yes, yes.
All right. So I'll increase it. So thank you very much. So what I'm going to present is the title of the talk, Improving Color Image Binary Segmentation Using a Particular Non-Negative Non-Low Rank Factorization, in particular non-negative matrix factorization. This is a joint work with a colleague of mine, Ciro Castello and Flavio Esposito from the same University of Bari. Before starting, I would like to thank the organizer of this workshop on mathematical methods for image processing and understanding for their invitation to contribute to this session. And sorry about the problem in sharing this. So first starting, just a brief outline of what I'm going to talk in this few minutes. And in particular, I'm going to illustrate some of the motivation behind our idea, which involve actually what a segmentation process is, and in particular, how we can represent a color image. Then I will concentrate just on the main idea, that is the integration of feature, in particular integration of image color feature, and how to do this integration. And we choose to do it using an approximation of the new representation of the color image. I will sketch briefly the pipeline of the approach we have thought, and just give some idea of how it works, showing you some preliminary numerical evaluation of this approach, and then I'll close the talk just summarizing what we would like to do in the future. So why do we want to segment an image? Actually, there are several motivation and also different application that will require it. And first of all, what a segmentation of an image is a process that allows us to divide a digital image into multiple segment or regions, representing different objects or sharing the same characteristics. So about the motivation that we follow to segment an image, or you can see here a face. So for instance, we would like to identify the face into the image, or we would like to identify the object inside the image. You can show, I show you here a picture of the plane in which the segment identify the plane, or the picture, a special picture in which the clouds are identified. And another idea was when we deal with the medical images, so in general in medical domains, and for instance, we want to select a region in the image in some areas which share the common properties, like in this picture, in which we segment a mole image, a mole picture, and we identify the picture in which the mole is present. Of course, there are many types of segmentation algorithms. We are not dealing to review this, but what I would like to point out is that each of them has its strength and its limitation, depending, of course, of the type of images and the desired outcomes one wants to obtain. What we want to deal with are color images, and color imaging generally contains more information than grayscale imaging. Several color imaging segmentation approach generally are based on pixel color feature, assuming that in distribution of pixel colors corresponds some meaningful object. We can represent the color image with a different color space representation. What is the color space for an image, it is just a 3D geometrical representation of color that uses 3 numerical values to characterize each specific color. We generally deal with RGB color space, which is the most usually used, but there are also different other color spaces, which from a mathematical point of view, we can say that can be obtained by RGB using linear or maybe nonlinear transformations. So when we deal with the segmentation process, in terms of segmentation result, especially, we cannot say that for all type of images, there is a particular color space representation of the image which outperforms the other. So an idea could be integrate a different color space representation and so different embedded properties of the image pixel. The idea of integrating data, integrating information should allow us also to derive a new global feature, enabling to better describe the color image. And in our idea is also to improve any segmentation process that you will be used to segment your color image. So what I'm going to discuss is how to derive a new global feature which are able to describe a given color image I. And the kind of integration I would like to support in this talk is the integration via low-rank approximation of the data matrix. In general, this slide say what a low-rank approximation is. So if we have a data matrix, the low-rank approximation of a general data matrix allow us to factorize the matrix, to divide the matrix into the linear combination of other 2 or more matrices, which share some property with the original image. In particular, when we are dealing with images, the main property of the images, the physical property is non-negativity of the intensity of the color, because we would like to start with the color images, or also the intensity of gray level pixels. So is the value of these data matrices are non-negative. So among the different low-rank approximation methods of data matrix, we can choose one that is able to preserve the physical non-negativity of in the pixels intensity of the data matrix. And this is the non-negative matrix factorization. In particular, the non-negative matrix factorization is the composition, actually an approximation of a data matrix which perform which obtain an approximation of our data as the product of 2 non-negative factors and with an additive sum of non-negative factors, which enable also us to interpret better the building blocks of these factors. As you see here, the building block will represent, in our case, the column of new factor W. Let us do this when we have an image. So let us start with an image I. Let us see it as a tridimensional non-negative data. So the 2 dimensions are the row and the columns, which indicate the position of each pixel into the image, while the third is the pixel intensity value of a color channel in which we represent the image. We decide to apply an operator, the histogram image operator, which actually derives some feature representing the number of image pixels which are found in each different intensity or channels in our color space representation. So when we start with this image I, which is a color image, we decide some way of representing in the color space. As I said, there are many color spaces, all connected each other. So what our idea is to borrow all information, particular information from any representation. We choose just, for instance, 4 color spaces, RGB, the chrominance, the luminance, chrominance color, and the color lightness of image from black and white and chromaticity with no limit, and also the HSV color space, which is a cylindric transformation of RGB space. And to apply to each of this channel, color channel, the histogram operator, just to derive the ambient histograms of each channel, the pixel intensity in the color channel. So in this way, we are able to represent or to obtain what we've called an enlarged representation of the given image I. The larger representation means that the new data matrix we deal with is a non-negative matrix in which each column represents the histogram of the particular channel in the particular color space that we have chosen to represent the image. So again, structures, non-negativity of the elements of the data matrix, columns are histograms in this particular representation, and what we would like to do is to integrate all different representations in order to extract some hidden properties from the image I. So what we are really integrating are the intensity, the hue, the luminosity, the color luminance, red and blue chromaticity, luminance, hue, and saturation, just because we have used this color space representation. Our data matrix is the same. The columns are the total dimension is the dimension of pixels we have in original color image, while the number 12 represents the 12 channels, color channel that we have used to represent, and then on which we have applied the histogram operator. And why do we apply the histogram operator? Because the choice that we did for the segmentation algorithm is the most simple one. It is actually the Otsua segmentation algorithm, but it will be explained directly later on. So starting from this enlarged representation, we call enlarged histogram matrix representing the image I, we apply Lorentz factorization. We do not care now about the particular algorithm that performs the approximation matrix, but we care about the result we obtain. So we are able to approximate this data image representation, obtaining two factors, the basis factor W and the encoding factor H. Both of these factors are non-negative. The dimension, of course, is reduced with respect to all the channels, and we are able to interpret the columns of the left-hand side factor W, the basis factor, as a meta-histogram information. We call meta-histogram factor because just it represents an additive combination of all colors histogram. So hidden information in the different color space are combined all together to obtain a new feature. These new features, the columns of W, can be considered either representation, color representation of image pixel, and can be used to perform the segmentation process of this new representation of the image. Here is just the pipeline, the general pipeline of the idea. So we start with an input color image. We represent and we choose different color spaces representation. And so we adopt different spaces. We use the histogram operator just to compute histogram for each color channel, which represents a hidden property of the image pixels. Then we construct a new representation, an enlarged matrix histogram representation of the image, and we approximate with the aim of extracting hidden knowledge from color properties embedded in this particular representation. Once we have the new representation, the new feature, global feature or ideal color representation, we applied in our particular case a threshold in segmentation. We choose the Otso algorithm to segment the image and obtain the final segmentation. representation. Actually, we test this pipeline, this idea. So I did not concentrate on the mathematical algorithms we applied to obtain the MNF. There are a plethora of different algorithms with different properties. What we did is just to apply the simplest Otsu thresholding methods on the result of the feature extracted by an enlarged representation of the matrix. And what I'm going to show is just the binarization of the results, because the main idea was, because we were dealing at the beginning of this work with the medical domain, so we were dealing with separating segments, particular part of the image from the background. And so we need to individuate inside the image some part that had some medical could have some medical interpretation. We also test some with some benchmark feature which had the true segmentation results, and so we were able also to propose some quantitative metrics to evaluate the idea, if this idea can be applied. And here is the first three images I'm going to show, just three benchmarks: a palm, there's some vases with flowers, and the well-known martini glasses, colored martini glasses. So that's the picture in which we have the original one. The simple segmentation, binary segmentation provided by the Otsu algorithm on the transformation on the gray level channel, and this is the binarization of what we obtain with the multi-level Otsu on the segmentation results when we transform the image with the four chosen color channel. We apply the histogram on histogram operators on each color channel, and then we summarize all the information, extracting some, we call it meta histograms, on which we can perform the segmentation algorithm. You can see, especially from the first and the last image, from the basis, also there are some artificial segment that we are still obtaining, that the results are better because in some way we are dealing with the hidden information that comes out. Just other couple of tests with the color imaging with ground truth, so table and vessel and more complicated running dog. On the right hand side, you can show what we consider the proper good segmentation of this image, so the ground truth against which we can apply the metrics that we have chosen. And I would like to point out about the metrics using the use of a new representation of the data, and the MNF in other words, and then on this new representation, the application of the also histogram in terms of accuracy of the result against the ground truth of gives some preliminary good chance that this idea of integrate data or data representation could be also work in a general context. Just another point about this approach, and especially with the MNF factorization, what we are also able to add to the features that represent the color image is a probability mask that is provided because of the low rank approximation of this new representation of the image, and which allow us also to give it new information as an input to any supervised algorithm to perform then classification of each pixel into the image. So these again are the results. On the right hand side, you can see the result that it's almost similar to the ground truth that we obtain connecting the information extracted by an and applied just the also algorithm. And this is again the same result for the vessel's information with the probability mask that we are able to extract reading the second factor I show you. So from the W matrix, we obtain a meta histogram, so a new representation of the image, while the matrix H codify some probability informations about the probability that pixel, because of course we maintain the meaning of the row and the columns of the vectorized image at the beginning. So we know each pixel which probability has to belong to the background or the foreground image. Just to some conclusions to deal with the MNF. Just the idea is integration, data integration, or data represent data in different way and integrate this different representation to extract as much information as possible. So what we have done in this particular context is to use color image information embedded in different color spaces, use histogram operators and apply MNF to compact this information to linear combined and to extract a more useful meta feature, let us say. The approach, because of the particular low rank methods, the MNF methods, is also able to produce a probability mask. As I said before, it could be used to feed the supervised learning algorithm to identify any pixel. You can choose different color spaces, and of course you can deal with the numerical parts, so choosing the rank and also choosing the particular model to construct and to approximate the particular algorithm, I will say, to construct MNF, and to deal also with the penalized MNF, so adding additional feature that could be also allow you to concentrate on part on the images, like also for orthogonality or sparseness, just to extract or to impose inside the mathematical model new property, qualitative but also quantitative property. The other idea, but we have not yet tested, is to apply directly to the color channels representation without avoiding, in that case, the histogram operator, and try then to apply any other segmentation algorithm instead of that, like also based on thresholding ideas. So that's all, and I thank you very much for your attention.
Do you have any question? There is a question.
Thank you for the nice talk.
All right, thank you.
Just a curiosity, why have you chosen exactly the Otsu method over the knee black, the Pansalkar one, and so on?
It was just for a proof of concept. It was the simplest one, so we choose this thresholding well-known segmentation algorithms. We are going to test other algorithms to do this, but it was just what I've shown you as the preliminary results we obtained, just to understand if the idea of integrate data, different representation, different color space representation of the image could produce some improvements on at least one simple segmentation algorithm.
Okay, thank you.
You're welcome.
Thank you very much. Now we pass to the next talk. It's a talk about affine difference based metric for magnetic resonance image imprinting by Marco Seracini.
Good afternoon. Can you hear me?
Yes, yes.
Perfect. I'm going to share the screen. Let's see if it works. Full screen. Can you see my my screen?
Yes.
Oh, perfect. I will put it in full screen, so it's even better. Can you see it?
Yes.
Oh, perfect. So good afternoon, everyone. I'm really pleased to be here, and I want to thank the organization committee, all the friends and colleagues from the University of Perugia. And today I will introduce an improvement concerning a kind of painting technique and apply it to magnetic resonance images. This work has been developed together with Professor Claudia Testa of the Department of Physics and Astronomy of the University of Bologna, where I currently work, and with Professor Stephen Brown of the Massachusetts Institute of Technology. He also holds a private company that is called Professor Lab, where he works for geophysics problems. So the first thing that I want to overview is what is the inpainting problem. The inpainting problem consists in filling an area, an unknown area or a missing area in an image, like the black one that you can see here on my screen, and we are going to denote it with the omega letter. And we want to fill these missing images in a plausible way such that a human observer cannot perceive the presence of an original missing part. And I point your attention on the fact that in this case, the evaluation is completely subjective if we do not have a ground truth. This point is particularly important if we are going to use inpainting methods, for example, for medical reasons, because in those cases, we want to be sure that the reconstructions exactly represents the reality to have a correct diagnosis of the tissue that we are going to investigate. So the missing area omega can have whatever topology and can be of whatever dimensionality, such that the inpainting problem can be joined with the wider class of problems that stands under the name of data bootstrap. Here in these four images, you can see an example, two simple examples on the left of images that we are going to inpaint. On the top one, there are scratches on the image, and on the right one of the same row, you can see the final results. And the same, another example is on the lower row. So there are different classes of methods used nowadays to solve the inpainting problem. I have made a summary, and I've grouped this. I can hear in background some noise. Maybe someone has a microphone that is turned on, or maybe it's just my echo. Okay, so there are three groups of methods that are used to solve the inpainting problem. The first one group the partial differential equation approach and gives usually blurred results in case of large missing area. And this method is also, in some sense, slow to find achievable result. And the good point of the partial differential equation is that we know the theory that is behind this kind of problem. Another group is represented by the functional minimization of solution based on functional minimization. And this is the group on which I will focus in this talk. These kind of solution are not particularly fast, except if you use some particular methods like the patch match that has been introduced in 2009 by Burns et al. But it gives promising results and also as a formalization that is better than the formalization that we have about neural networks that represent the third class of solutions that are available for this kind of problem. Of course, every one of us know neural networks. We know that we are extremely fast. They provide good results, but they miss a complete mathematical model. And this is the reason why in the mathematical establishment, they are not seen with sympathy, let me say in this way. So the second group of solvers that I have introduced in the previous slides use what is called also a method referred as inpainting by patch. The inpainting by patch consists in, suppose that we have a missing area in the image. The area is omega here, so that is just the black one. And we can also, we want to, in some way, inpaint this point that is the red point. What we do is just we choose a neighborhood of the point that we want to inpaint. We scroll the neighborhood all over the given part of the image, and we go to minimize the, we go to choose the best fit, the point around which the neighborhood is the most similar to the ones that is given in the area that we want to define. The given part of the image in this way represents what we can refer as a training set, using a name that is typical of neural network. So to calculate the similarity between these patches that we are going to use, we have to introduce a distance. Here I've denoted it with D, and in this case, of course, we can use whatever kind of norm that is available in the mathematical literature, but here we are going to use the L2 norm. We perform the sum of all the differences of in the neighborhood, and what we want to do is to find the solution that minimizes this sum. This is also referred as finding the minimums of a functional that is called inpainting energy, that has been introduced by Demanet et al. So despite its conceptual simplicity, a complex behavior is hidden in this kind of method. In particular, we have to choose the best metrics to estimate the similarity between the patches. We have also a problem concerning the scanning order. We have to move in the area, in the missing area, such that we want to maximize we want to minimize the uncertainty when we are going to choose the best fit. There is also a problem connected with the size and the shape of the neighborhood that I denoted with key here. And of course, there is a problem that is inside the size and the shape of the unknown area omega. So what we want to do is the problem consists in the fact that we can have multiple equivalent solutions when we are going to find the minimum of the inpainting energy, and such that we want to introduce other constraints to reduce the number of these multiple equivalent solutions. Another problem is connected with the fact that finding the minimum of a sum is not equal to find the minimum of each term of the sum. And this is an uncertainty that is due to the shape and the size of the neighborhood. And moreover, the final solution depends also on the initial conditions. In fact, most of these methods generates a random values that then are going to be refined to find plausible solution. So our idea is to introduce finite differences in the expression of the inpainting energy. This is a toy model example where three functions are represented. The reference function is the f function that is equal to 0.5 between -1 and 1. The second function is g that is equal to 0 between -1 and 1. And the third function is a function that is equal 0 between -1 and 0, and is equal 1 between 1 and 1, such that it's just a square wave. If we apply the impending energy, what we are going to calculate is the yellow area in the left image and the red area in the right one. Then two completely different functions can be not discriminated by the impending energy. And this is because the function f has the same rate of similarity with the function g and the function h, even if they are clearly different each other. So what we want to do is to introduce the finite differences, directional finite differences. Of course, the availability of these finite differences depends on how big we take the neighborhood of the point that we want to paint. And we can define then another energy that is connected with the finite differences. And this is the expression. It depends, of course, by some parameters. And in particular, L denotes the maximum order of the finite differences that we are going to use. Theta K represents the set of available directions. Rk is a set of normalization terms depending on the cardinality of theta k, and beta k is a set of dimensional. It depends on. We have to normalize the dimensionality of our problem. So we can you hear me? Because I cannot hear.
Yeah, we can hear you clearly.
Okay, perfect. So what we can do is that we can reformulate another impending energy, and this energy is given by the sum of the previous impending energy that here we define as a content term, because it is connected with the content of the image. It is connected with the color of the image. And another term that is connected with the structure of the image. And we intend here the structure like the derivatives, the shape in 3 dimensions of the image itself. So we can see that there is a strong connection between the content-related term and the structure-related term, because also the content term contains information about the structures. And on the other way on, also the structure term contains information connected with the content. So here is an example of the equivalent points, equivalent patches that we can have when we when we use only the impending energy connected with the content term, and it is represented in blue. This is the number of the patches, and this is the size of the support of the neighborhood. And as you can see, adding this new term, here we stop at the first derivative, and here we calculate the second derivative. As you can see, the number of available patches drastically decreases, such that the probability to make a mistake in choosing the correct value is going to decrease. And the probability to make a mistake is basically 1 minus what you can see here in this other graph. The certainty, the trustability, this is represented the trustability. Okay, we can also using some tricks to make normalization of the distance and some other technical mathematical operation, passing, for example, to and exploiting the property of the logarithm, we can give a statistical interpretation of the impending energy. I have omitted the details here because the time is not enough to explain everything. So when we are going to switch from the sum using the logarithm properties, this sum becomes a product, such that we have a sort of product of probabilities. This means that we are making an hypothesis of statistical independence in the formulation. And this also means that dropping a not equal to one term in the products is equivalent to say that I know exactly what is the value of that point. And this is not always true, and this is causes of problems in the painting procedure, because the error are going to propagate. So what we have done here is that we have taken some phantoms that are objects of well-known construction characteristics and geometry that are used for calibration in magnetic resonance. So what we want to do is to take the image of a set of phantoms, to delete some zones from them, and to perform the search of the missing part in the pristine image, such that we expect that reconstruction has to be without errors of any kind. To check the similarity between the achieved result reconstruction, we used the peak signal to noise ratio. So our goal is to study the effect of a finite difference term in the formulation of the impinging energy in the direction of the quality and the reliability of the reconstructions. So here are the two sets of phantoms that we have used. The first one is achieved using a T1 sequences in magnetic resonance. The second one is achieved using the T2 sequence. And I point your attention, here we have used the Weber contrast to quantify the contrast of the image. All these images here in the first row has the maximum contrast, while in the second row, the contrast, especially in the second, third, and fourth image, is not the maximum one. So we have a lower contrast. This is just the expression of the peak signal to noise ratio and of the Weber contrast, but I assume that is noted. And these are the visual results that we achieved. In the first line, we have the ground truth. In the second line, in green, are highlighted the missing area that needs to be painted. In the third row, we use just the painting energy without the introduction of a structural term. And you can see that there are artifacts here. Here is missing this point, and also here it is not perfectly round. These are the results that we achieve using introducing the structural terms. And as you can see, the results are identical to the pristine image. This is another example using the T2 sequences. And as you can see, we have the same problems and the same results. And here we are going to see what is the result in terms of peak signal to noise ratio. And here you can see in this column, what is the order of the finite differences that we have used. And the interesting fact stays in the fact that when the contrast is maximum, only a first order derivative is enough to achieve the pristine image, such that we have a peak signal to noise ratio equal to infinity. But when the contrast is not the best, it can happen that we have to use finite differences of higher order. For example, this is a typical example where we needed to introduce the third order derivatives. So in conclusion, the introduction of the finite difference terms improves the quality of the reconstruction, guarantees a faster and more regular, meaning less oscillations, convergence of the energy functional to a lower minimum, or anyway reduces the number of available minima, and allows to achieve back pristine images if the missing part of the image is available in the search domain. In addition, lower the contrast of the image to reconstruct is the order of the finite differences needed to achieve back the pristine image. Thank you. Can you hear me? Because I cannot hear you.
Yes, we can hear you clearly.
Perfect. I cannot hear maybe the main stage, let me say so. I can hear Giulio, but not Ivan.
So microphone
Okay,
from
now
okay. Now we can hear you.
Can you hear
No,
me?
I can hear Giulio.
Thanks
But
for the nice presentation.
Okay,
I
now I
just
can
want
hear it.
to ask one thing. Can you go to slide number 19?
I am not heard what you said. What number
Slide
19?
number 19, yes.
Okay. Okay, I'm going to share the screen again, I hope. Okay.
Within this, with those.
Yes.
You can't see this.
Just a moment. Is this one? 19.
In the middle line, when the structure is removed in the middle line, the column, the middle column, when the structure was removed, how it was recovered?
Oh, this is because, as I've said, if I got the question, the green is removed, but we are going to train the we are going to search for the correspondence in a training set that contains the missing part of the image.
Yeah, but it is a totally different structure which was missing in the image, which feed
Yeah.
the middle one. I'm asking the column, the middle column.
Yes, this.
No, the second column.
The second
Yes, in
column.
the second column, this one.
Yeah.
Yes.
Okay,
So in this
here
column,
this part is missing, but we have performed the search in this image, not only in this neighborhood, in the whole image. And what we wanted to prove is that even if you know exactly what is missing, that is this one, this that I'm highlighting with the mouse pointer, if you don't use structural information, you will have errors in the reconstructions. Okay, we have trained our system. Let me use this expression typical of a neural network, using this one, such that we have the missing part of the image, but we have reconstructed only the green part. I hope it's clear.
yeah, so it means that we have to provide the original image without the missing part.
Yes, we have used the original image to find the best correspondence. But as you can see, if you don't use the structural terms, the best correspondence due to the equivalence classes that we have performs an error because it is not able to reconstruct what is missing. Even if it is pleasant for an eye, you cannot say that this one is a fake image, is reconstructed. But this is important in medical images because we want to reconstruct something that corresponds to the reality of the fact, not only something that is aesthetically nice to see.
Yeah. Thank you. Thanks for.
You're welcome.
Thank you. Now, before to present the next talk, I have to say that since we have to left this room at 5:30, I cannot able to present my talk. So I invite you to write me, and I will present this talk next Wednesday at 10 of the morning on Teams. And just you write me an email, I will connect everybody, ok? Non lo so, adesso c'è... No, perché c'è un altro.
Now Sani Akhtar should present the paper, I guess.
Alla DU. C'è un altro. Again.
Can you do it, maybe move it to the next room?
Yeah, but I think that if we can See, in a week it's the same. I will present the stuff to all the.
It's for the live conference.
Okay.
The thing is that all the talks were already late, so
This
give me a second so I can talk with Julio and find out what we can do. Hey, Julio,
Yes.
can you hear me?
Yeah, sure.
Yeah, sure. Okay, we have another talk here, and I can. There's another guy to come and chair for the chair and for the technical assistants in this room.
Okay.
Okay, until they will start probably the other room, I guess. So yeah, they're here. Let me check if they can move. We can move a talk.
Okay, because we have one talk left, the one by Sania Akhtar, who is waiting for instructions. So
let's do the last talk in the one. So the last talk is about automatic urine segmentation, detection, and classification based on ULO-8 algorithm. It's presented by Sania Akhtar. Do you listen me? Hello, Sania? Giulio c'è?
Yes, we spoke till a few minutes ago.
To do your presentation, but in a shorter time. So until the next one was supposed to start at 5:30, and you can you finish by 5:40 at most? It's 15
Yes.
minutes. Can you start?
If
Is
they
it okay
start,
for
they
you?
should
Yes.
start.
No, it's from you. Do you have your paper?
Yes.
Right?
No, there is another girl that is talking now, and before me.
There are two presentations?
Yes.
How many presentations were there in the session?
This morning we was long, and we didn't do my presentation.
Oh, so your presentation was supposed to be in another session?
This morning.
Okay.
But we finish as now later.
Yeah. Okay. Question for the other girl: is it possible to finish the presentation by 5:40?
I am texting privately, and I told to finish in 15 minutes. So
what? Sorry.
I told Viofor that the presentation should last 15 minutes, and she is supposed to start now, but I cannot see any screen share as of now.
I can ask her to finish in 10 minutes.
Yes.
But where is she?
Can you unmute her?
Where is it, Sonia? I can't. Julio, can you unmute Sonia? No.
I'm already texting her. I told to start.
Sania, can you hear me? Sania.
She's not answering. And I don't have the moderator.
Sania, can you hear us? Sania?
She cannot hear us.
If you want, I can present my presentation very fast in 10 minutes.
Can you do that?
Yes.
Maybe move.
Yeah, please wait.
To the next one or something like that. I don't know.
She is not responding.
Okay, so.
Can you Yes.
Yeah.
Yeah.
It's
But
the one
wait,
that I
it's
give
this
you.
one, right?
Yes.
Okay. The thing is that we have something like 10 minutes. I'm sure about that. Let me share my screen. Share screen.
Ivan, are you going with yours?
Now, faccio la mia adesso, dai, faccio veloce perché c'è già gente che aspetta.
Allora rimanderemo un'altra sessione e manderemo informazioni.
10 minuti la tiro via.
Sorry about that. Okay.
Okay.
Let's start.
Hello. I'm Ivan Gerace, and this is a talk about source separation.
The next speaker is Ivan Gerace from the University of Perugia,
Yes.
which will talk about the mathematical, which blind source separation of color noisy blurred images. Thank
Okay.
you.
So let's start with the model. In our model, a document we consider as a document the front of the back and the back of the a document. So we use a matrix. Well, the first three columns are of the front of the document. The last three columns is the back of the document. Each column is a different channel, so that we consider a different blur for acting from all the channel. In particular, there is two kinds of blur. One is the one that acts of the main part, and the other one is the blur that acting in the reverse part that is featuring in the above document. Then we consider this kind of model. We have the source document that is before blurred and then mixed with this blur matrix, and we define this operator, this total operator, as the operator HIS. That means that before we blur the document, after that we mix that. And we consider also an additive noise. The problem consists in try to find the original sources, having the data set, and we assume that the missing matrix A is unknown. To solve this problem, first we start with the non-blind problem, in which we consider the missing matrix A known. In this case, it's still an imposed problem, and we try to regularize the problem using a second order finite difference. This finite difference are defined in a clique. A clique is a set of three peaks adjacent in horizontally or in vertically way. And the definition of the second order derivative is this one. This is the classic one, second order derivative. Moreover, we add in our regularization model the non-parallel constraint. These constraints, if we use this constraint, we obtain a result like the one here, not the one above, because you notice there are some double parallel line, and so we penalize this double parallel line. To parallelize the double parallel line, we have to define an order of the clique. So I need to define which clique is adjacent to the other clique, because if there is discontinuity in one clique, we don't want there is discontinuity in the adjacent clique. Then we define the following energy. In this energy, this is the classical consistency data term. These two are two terms related to the derivative. They are regularization terms. In particular, the first one consider the derivative of each channel separately. The other one consider the difference of the derivative of the different channel, because we want that the derivative of the channel should be the same in this. And the function here, the function phi, is not quadratic. We consider that as this form. This form is ideal to avoid parallel line. This is why this function has two terms. But this function is not convex. So when we minimize the energy function, we start from this function, and during the minimization, we transform this function in this other one function. This technique is called graded convex algorithm. Now we consider the blind problem. In this blind problem, we define this matrix as the minimum of a particular target function that consider the mixing matrix and the solution of the problem. Consider A as the real matrix, and we find the relative sources. We call this technique indirect maximum a priori, high map. And for the target function, we consider different terms. The last two terms are the same as we see before. This is a non-Gaussian terms that I will describe later. This is an overlapping term, and I will describe it later. And this is the entropy term. Let's see what they to minimize this target function, we use a simulated annealing. So the computational costs are very high. In each step of the simulated annealing, we call a gradient non-convex algorithm to minimize the energy function for the non-blind problem. We define this technique as Betty's blind estimation technique, imposes smoothness and non-overlapping, and because we paragonate it with another technique that we use some years ago, called Betty's blind estimating technique, imposing smoothness, in which we didn't use all these terms like non-Gaussianity, the overlapping term, the entropy term, and the fact that the derivative should be of the second order. This is an improvement of the last algorithm. Then, for the Gaussianity, we want to find the distance between the histogram of our image and the Gaussian that are more closer to them. This is not an easy task because this function is not convex, and we implement it by simply heuristic, just because to not increase the computational cost. And the measure of the non-Gaussianity is this one that you cannot see. Okay. And as regards the overlapping constraints, we know that in general, we consider that the right of the front of a document is difficult that are the same of the right of the back of the document. We consider the measure of how much the letter of the back are in the same position, the letter of the back as the overlapping measure. Sometimes the letter overlapping. So we defined in another article a method to estimate the correct overlapping of the two documents. So we start with this fast algorithm that gives us the correct overlapping of the document. And here we impose that the overlapping of the document should be exactly this measure that we estimate. Then for the entropy, it's well known that when we mix, we blur, the entropy of the image increase. The entropy is the number of the states. So here we have more line. And we use the classic formula of the entropy here above that where K is the Boltzmann constant. To show that the results are better than our last past algorithm, we use the same data that we used 5 or 6 years ago. So we consider this blur matrix, and this is the result. Now, that's the original image. We mixed them synthetically in this is the measure. These are the separation that we obtained before. This is the new you can see here that we improved the quality. This is two images of the planar mixed, and here the results are much better than the previous one. This is another image. You can see here the improvement. They are practically the same of the original one. This is the real mixed images, and you can see that the new estimation is more closer than the one that we obtained some years ago. And here, there is a very large improvement of the MS in the results. This is a real image. I obtained it by scanning the paper, and there was a show-through effect. And this is the result of the previous algorithm and the new results. And for the last, we use this document. This is a document about static writing that are in this project. And you can see here that here just the new algorithm. I didn't test the last one algorithm, and we obtain quite good results. Thank you for final words. We can estimate both the mixing matrix and the blend matrix as a new. But in this case, since the space of the freedom of the variable are increased, there will be a large increase of the computational cost of the simulated algorithm.
Thank you. Are there any questions? Yes?
Yeah, thanks for a nice presentation. Really nice job, especially unmixing the images. That's quite impressive. Can you go to slide number 27?
27. Yeah.
How you reconstruct the background of reconstructing it? You separated both the classes?
The background is well reconstructed because I use a very large regularization parameter. In this, in the formula of the function phi, there is lambda that is the regularization parameter. I put it very large, and they when it's very large, it tries to make a very flat area.
Okay, so what I understand is that you first separate the whole image, which is the RGB of the right. You separate it into three classes.
Which lines?
So the image on the right, on the left side.
On the left side, this one.
Yeah, the original image. So you the mixture. How many mixture you consider?
And on here, the problem is that when you mix a document, the image on the other side is split. So here there is not correspond, but this one is this. It's because you have to flip the image to understand.
Yeah. So you take two classes. What is the background?
I see background and the front, the mixed, and I want to find the original back, front and back.
The foreground. Okay, the foreground again.
No.
The whole. Okay. It is the separation problem, right?
Yeah.
How to separate sources?
The sources.
Information. How to separate different information.
Which information this express?
One is the foreground text, right? The foreground text. Another is the bleed through.
Yes.
And the third is the background of the paper.
It doesn't recognize the background.
Okay.
No.
The background is an average value of the. I suppose.
Dai, che sennò questo ci ammazza. Aspetta.
Yeah, so you can. Thank you.
Any other question? If not, we can begin the speaker.
Sorry for the delay.
Okay, sure. Okay, we will start with the next session in about 4 minutes.
To close.
Okay, you can talk until we do that. It's already unmuted.
I would like to thank all the participants of this workshop of mathematical method for image processing and understanding, for having participated to this kind workshop. Thank you very much.
I think we've already got it. Hi, so we will start. Okay, we will start in about 4 minutes. We are rejoining from another computer.
Marco,
Sì,
Marco, buon pomeriggio, mi vedi?
no, ti vedo oscurato.
Ah, perfetto. Mi collego un attimo con il mio computer.
Sì?
È il tempo di collegarmi con la LAN e siamo di nuovo connessi.
Perfetto, ok, dai, io ti aspetto qui.
Perfetto. but
Okay.
now I move.
We will be back in 3 minutes with HDMI for you.
Marco? Marco, mi senti?
Sì, perfetto. Ok.
You will need power.
Ciao Luigi.
Yes. Let me fix your microphone. You will need power. It will shut down. Can you hear us? Wait. Can you hear us?
Yes.
Okay, and it's the thing. It's about the
No,
sound.
altoparlante.
No, this one. Can you hear us now?
Yes.
Yes.
This one? No, it's this one. I want the top. Okay. They can hear us. We can't hear them. I think that the mic is okay. Or sound. I think that you don't have. Like, remember this. Remove this one. Can you remove it for now? Remove it at all. Okay. And then just change it. Really fine. It's not working to test it. Is this one? Oh, and remove this one. Remove this one. Okay. About the microphone. The thing is that the microphone is this one. What's this? Do you have a? Where's your sound? Okay. I can't see. Can you find your sound? Sorry, I'm not good with you.
Now?
I can hear you. The thing is, we don't have sound.
Sound.
If you put the sound in your computer, stop it.
Now it's my word.
Yes.
My word.
It's your test, so we can hear you. This one. Ah. Can we leave your computer as you did before, that it works?
Okay. And now can you hear me?
Marco?
Sì, eccomi, ti sento.
Ok, lavoriamo con l'audio del mio computer. Possiamo partire quando sei pronto.
Ok. Ascolta, lavoriamo con l'audio del tuo computer, significa che le presentazioni di chi ha avuto problemi?
Yes,
O no?
No. All virtual hear us, all virtual presentation.
Okay.
Only people in this room hear the presentation from my PC audio.
Okay. Well, we can start. Good afternoon to all gathered at this conference. We are about to start the SAMLUM and VRA sessions of the conference. So we can start with the papers listed, which will be presented to the audience. The first presentation of this session is GIS referenced methodological approach for the brownfield redevelopment by Alfonso Ippolito, Yasmin Selim, Francesco Tagliani, Rossana Ranieri, and Pierluigi Morano. Are you ready to present?
Yes, Professor.
Okay. Well, good. You can proceed.
I'll start sharing my screen.
Yes.
Tell me when you can see it. Okay.
Please.
My screen is visible now?
Yes, it is.
Okay. Good evening, everyone. I'm Yasmin Salim, and I'll be presenting the research titled with a GIS reference methodological approach to the brownfield redevelopment, written with cooperation with my professors, Alfonso Ippolito, Francesco Tajani, Rosanna Ranieri, and Marco Lo Crucio. And the research roadmap is divided into the identification of what are the brownfields, what are the possible uses of brownfield sites, mapping the exploration of all the vacant abandoned sites, the framework to help the decision support for reusing brownfields, and finally the analysis on a small case study using GIS mapping and analysis. Following the concept of Anne Lacaton, never demolish, never subtract, always add, always transform, trying to using architecture for solving the issues of all buildings and societies. The difference between industrial heritage and brownfields is industrial heritage, according to the Dublin principle definition, is that it's all structures, complexes, and landscape related to machinery and all documentation related to industrial processes that existed. The difference is industrial heritage is a well-preserved, well-used site, but brownfields is sites that were impacted or affected by the industrial use, but never taken care of. Mostly they are contaminated site that needs remediation before reuse. The current situation of the industrial heritage is usually looked at in a negative image because of the industrial urban landscape around them, the rough statics and the heavy industrial architecture, and the pollution that comes in the site. The deindustrialization crisis impacted and enriched this negative image of the industrial heritage, leaving many complexes abandoned and run down. According to the Eurostat statistics, 14% of the land uses in Europe are empty lands, abandoned lands, and usually these lands are placed in very desirable waterfront areas or city centers. So using these are enormous potential for the cities and the development of the areas. Targeting with this research is the alteration of value of the industrial heritage by adaptive reuse, the barriers and the benefits of the brownfields redevelopment, the creation of a database or an inventory for the brownfields using GIS, including both the governmental and investors' decision support help. Finally, a framework to lay the foundation of the brownfield redevelopment. The main keywords are decision-making, GIS, industrial heritage, brownfields, sustainable conservation, and framework. The necessity of brownfield reuse started to show after putting it into consideration in the ICCMOS and the International Committee of Conservation of Industrial Heritage, acknowledging them in both the Nizhny Tagil Charter and the Dublin Charter in 2011, addressing how highly vulnerable they are because of the lack of awareness, documentation, recognition, or protection of these areas, changing the economy trends into a negative perception and the negative environmental issues that comes with them. This is a timeline of how the awareness was changing according to the years. By the 1960s, with the end of the Industrial Revolution and the deindustrialization of many buildings, leaving them abandoned, this started to create a birth of industrial archaeology. A large scale of these buildings were demolished or abandoned more in the 1980s. By the mid-1980s, people started to notice how they're creating an environmental issue and started addressing and reusing some of these industrial heritage buildings. In the early 2000s, there was an industrial heritage reuse structure coming with the Nizhny Tagil Charter in 2001. After the financial crisis in 2008, the reuse of these buildings decreased a little, but after that, according to the Dublin Principal Charter, there was more regulations of reusing this industrial heritage and how to benefit from them, so it saved them a lot. One of the Dublin Charter principle was by extending the life cycle of the existing structure by embodying their energy and conserving the building heritage. This can contribute to achieving the sustainable goals, not only on the local, but also on the national and the international levels. And it doesn't only touch the social, but also the physical environment that impacts this heritage. Studying the goals of reuse, it was matching the sustainable conservation, impacting the economy, society, and environment. Both of them have common goals with heritage, raising the awareness of appreciating the industrial heritage and changing the negative perspective, impacting the environment by recycling the building and reducing the waste of reusing them, and just changing the impact of them on the community, the social well-being of the community by adapting them into more accessible, more usable public spaces, and the heritage management, which will come with a huge benefit for the government and the private sector if they invest in the redeveloping the brownfields. The phases of any adaptive reuse project is consisted of mapping, creating an inventory, knowing all the available sites, but also including the important data according to it. So the site ownership, the site situation, and every detail related to it. The visualization of these data, not only using the maps, but also using the surveys to collect the bottom-up ideas of how the society will benefit from reusing them. The decision-making by creating this inventory, it will be very economically helpful for the government and the society to and the investors to benefit for it. And finally, evaluation by creating a feedback mechanism, either online or with the community surveys, to see how are the potential modification of the strategy of reuse. What caused the negative image of the industrial heritage is the post-industrial society. The need of big spaces for big machines have changed. We need more flexible spaces for education and culture now. So changing the vision of the building into the flexible space that can host the contemporary culture or educational uses is one big benefit of reusing the brownfields. The alteration of values not only will impact the the economy, the feedback of the buildings, but also will help sustaining the conservation, and also changing the perspective of the industrial heritage overall, leaving these buildings from changing these buildings from being ugly, abandoned, and decayed into more flexible, more big spaces that are addressing the needs of the society we live in nowadays. Lastly, the culture consumption of these industrial heritage building had a small issue of not focusing on the historical essence of the building, but only focusing on the culture sold inside it. So we need to address the fact that highlighting this historical importance of the industrial heritage and the artistic value of the culture sold inside it, by blending the boundaries between these two things, will be a huge benefit, not only for the cultural, but also for the industrial heritage being reused. This was a small map of Europe with the successfully reused industrial heritage sites in Europe. Using GIS, it was located according to the coordinates and mentioning the previous ownership, the current ownership, and the location, who's running the project now. And all of this shows the importance of using the GIS in documenting all the buildings. This is one building in France that changed from being a factory of fabric to being a museum run by the Réunion du Musée Métropolitain in France. Decision-making is a big part of the business world, and it's well established according to Sauter, 1997. Doing the decision-making, there is always barrier in the redevelopment, because greenfields, it's only the sale value, land cost, and build cost equal the profit. But in the case of brownfields, there is always remediation costs that we don't know if how much it will cost, and it differs from one project to another based on how contaminated the site is and how much of intervention it needs. Is it only machinery? Is it oil expansion? Is it water pollution around the site? So all this impacts the remediation cost, and this impacts the progressive elaboration of the cost, which makes it a bit harder to break into the barrier of brownfields renovation. This is why the creation of a framework for the stakeholders was much needed, because the framework will help evaluating the project, the convenience, in a short time, that it will shorten the time that we need for the decision making, but also attract funding from different resources that can help redevelop as much projects as we can. The benefits according to each stakeholder, from the point of view of the investor, it will analyze all the possible projects, and it will cover all the unsure parts of the financial convenience. For the municipality, it will generate an accessible database that will help incorporate not only the investors, but also the city planning and the urban planners. From the point of view of urban planners, it's setting up the priorities, creating methodologies to empower the community and the owner. The NGOs will benefit from how the society will benefit and how this address all the environmental issues related to the brownfield sites. And finally, the community, by generating the best use possible for the community based on the neighborhood needs. The framework was based on many criteria, and this is some of the answers, or like how to find the answer for some of these criteria. The land area, how big the site, is it enough for a specific project or no? The existing contamination, as we mentioned before, this will impact the cost of the project. Will it have a small remediation cost, a medium remediation cost? Will we need external help from the government, from the investor? Can it be a collaboration? And this will decide the running cost of the project till its opening. The land use and land cover, is the site vacant? Is it owned by anyone? Is it owned by the government? Based on the location survey. Also, like if it have any current use, is it possible to change? Is it already good for the community? The land value is not only the purchase cost of the land, but also if there is remediation cost, if there is rental cost. It depends on the survey, depends on the data coming from the government. Is there any incentives from the government, from the local financial incentives, to help and attract more development on the project? Who are the targeted users of the area? Is this site already causing a lot of problems for the locals of the area? Is it causing environmental issues? changing this will attract more users for the area instead of it being abandoned. The appropriate zoning is the decided use impacting matching the proposed city planning, not only from the municipality side, but also with the urban planners. Is it collaborative use between all the partners to reach the most convenient project for everyone? The population demographics, community involvement, all these will help with creating more job opportunities, creating a safer environment for the neighborhood inhabitants. The proximity to transportation and the existing of previously existing infrastructure. Most of the brownfield sites, because they were existing in the city center and the waterfront areas, they already have infrastructures and they are already very close to the transportation, but how convenient is it to be connected to the city? So the framework is have these 6 steps with a specific order. So like target the geographic area, importing all the data possible, not only from the municipality with the land use, local information, but also from the neighborhood, knowing the ownership of the project and all the related documents to it, identifying a specific brownfield that we want to work on, to start applying the multi-criteria analysis on it and deciding which is the best use for this, categorizing the site based on marketability, because if the project have a high marketability, it will probably attract the private sector for investing in it. If it have medium marketability, it will attract partnership between the public and the private, and low marketability projects will mostly be run by the public sector. Screening the potential community benefits by using the site and neighborhood surveys, not only by the local surveys in the community, but also using the technology of the GIS by allowing online surveys for the locals from the area to participate into gathering more data. Evaluating the impact of the cultural development, since we noticed most of the industrial buildings have been reused culturally as a museum, university, or other cultural uses. Is this use more useful for the area, for the investor, and for the government? Is there any other proposed areas? Because mostly because of the contaminated fields, it's not good to use it for residential, but is it better to use it as commercial or as cultural? Lastly, develop the strategies using the feedback system and changing the financing resources and impacting this on the action plan. One of the sites that I applied the GIS methodology on is Exfiera di Roma. It was a previous industrial area in Rome. Now a part of it is turned into the police cars museum, and a lot of it is abandoned and unused, and it's causing a bit of distress in the area because it's in the middle of a residential area, as showing. Because as the city grows, the parts that were on the edge of the city being industrial turns to be in the city center with the urban sprawl of residential buildings around it. This is a photo of the building, and the analysis was consistent of the transportation proximity, the metro stops, and how close the distances between every metro station and the site, and how convenient is reaching these metro stops. And
Excuse me, could you go please to the conclusions?
Yes, I'm reaching the conclusion now.
Okay.
It's only a simple application of the GIS approach on how convenient we can see different data, not only from the urban point of view, but also from the demographic point of view, from the water contamination point of view, the distance between the inland water, and how this can impact the site. These are some of my references, and thank you for your attention.
Thank you. Is there anyone who has who has questions for her? Not anyone? Okay. Thank you very much.
Thank you.
Really appreciate your presentation.
Thank you.
We can proceed, and next presentation is a methodological approach for the assessment of parametric costs of sustainable urban roads, an application to the city of Rome, Italy. And we have Spartaco Paris for the presentation, I guess.
No, it's me. Good evening. I'm Rossana Ranieri.
Okay, Rossana Ranieri.
I will present the research. I'm going to share my screen.
Yes, you can proceed.
Yes.
Thank you very much. We can see your screen and you can proceed.
Thank you. So the research was carried out with a joint venture with expert in the architectural technology, Professor Spartaco Paris and Professor Elisa Pennacchia, and with Francesco Daiani and Felicia De Lido, that are specialists in assessment and valuation. The presentation is organized as follows. I will go as quick as possible because I know we are quite late. So the context is referred to the maintenance of urban roads, because as all we know, the urban roads has a really huge impact on the sustainability of the cities in general, and the maintenance of urban roads and in general roads infrastructure is a very intensive process that could really affect the quality of the cities, both from a sustainable point of view, but also from an aesthetical, cultural point of view. So having specific tools that support the public administration in order to choose better solution regarding urban roads and streets could be very useful. This research has a specific aim in order to, as I mentioned, in order to support the public administration and propose a methodological approach for the assessment of specific parametric cost for innovative technological solution. And the final aim is to compare the parametric cost that I will explain how we are going to calculate, and to compare with traditional solution in order to understand which is the differential in terms of costs between innovative and high-tech solution and traditional one. And this could be very useful for the public administration in order to enhance the public tenders, especially referred to the maintenance of the streets. This research was carried out with using 20 streets as a case study in the city of Rome, and we help the Roma municipality in order to define some strategies to choose better and innovative solutions. The methodological approach is composed by 5 main phases. The first is referred to a systematic analysis of the public tender procedures that the public department has been used during the years in order to understand which are the main typological materials, the main typological solution, and of course the phase 2, the goal is to define specific parametric construction costs for those type of typological solution. Then, according to the 20 streets chosen as case study, we define a parametric cross-sectional cost for a single meter of every type of street. And then we calculate the cost for the solutions that are innovative, and at the end, for each of the 20 streets of the case study, we calculate the differential between the costs, parametric costs for the innovative solutions and the parametric cost for the standard solution that are referred to the analysis of the tendering procedures done in phase 1. So the analysis, the phase 1 outputs give us a lot of information about how the resources in the hand of the public administration are used in order to maintain the streets. As you see, the layering and the binder are the main working categories that really have a huge percentage of incidence of the total cost of intervention in all the tenders of the last 10 years in the Rome municipality. And this phase also gives us the possibility to define a list of new prices according to particular working categories or particular solution for the streets that we find for the case study. The second phase is give us the information about the type of performance solution for each type of intervention that the municipality made on the streets. So the superficial, the medium, the deep, and the TBs that is like an alternative to the deep. So we have four types of performance solution, 3 types of categories that identifies the main objects, we could call them, the main objects of the streets as the sidewalk, the paved pavements, and the road paving. And then we have 5 main type of materials that the public administration ordinarily use to maintain our streets. So those are the categories, and based on these elements, we calculate for each type of categories the cost for the traditional solution. This is an example. Of course, we have a huge amount of different solutions, and this is a simple example for the superficial type of work. And we have found that of course, the price are referred to the Lazio Region 2022 price list because, of course, they are public tenders. And this is, for example, has a total cost for square meter of almost 48 euro for square meter. We made this calculation for each type of works and for each type of materials, and here we have just an outlook of the solution. As you see, the calculation show as an example is in this side of the table. So we have all the costs for the traditional solution, and then in phase 3, we try to calculate the cost for the designed innovative solution according to the indication of the technologies, of course. The technologies give us information about the performance that they expect to the materials for each layers of the working categories, and we calculate the cost for all the design innovative solution, and then we applied both the costs from the traditional and the innovative solution to all the 20 streets used as case study. Just a few information. The streets are spread in the city of Rome, and are identified in two main categories. The local ones, so small streets with a length quite short, or bigger streets that here, as you see, are called main streets, that are quite long and has a different side of the payments. So this is in order to understand how the innovative solution could affect the maintenance of the streets, and if there is a huge differential between the traditional solutions, so the maintenance made with traditional solutions, and the maintenance made with innovative solution. This is very important for the public administration because, in a sustainable point of view, it's very important to understand that sometimes an innovative solution doesn't cost so much related to the traditional one. Because, for example, the conglomerate bituminous, if has just few performance that are more sustainable, doesn't cause so much respect to the traditional conglomerate. Of course, very different, and this is a case, I put this example just to show where we have a huge difference between the traditional and the innovative ones, is when we change the materials. So for this example, this is an example of Via Conteverde. It's a main street in Rome, but the innovative solution designed by the technologists would like to change the materials. As you see, when you change the materials from the conglomerate to the basalt, we have a huge difference between the innovative solution and the traditional one. So we made all this calculation, both for the traditional and the innovative, for each of the 20 streets, and we calculate the difference for every streets. Of course, these 20 streets are particular and are going to be used as a prototype study. As you can see, sometimes the difference is very low. Sometimes, as I say, for the first street, that is Via Conteverde, or for the 9th street, the difference could be very huge, but this is because the designer prefer to change the materials according to the study, from the heat isolation, from the drainage performances, and they decide to change the materials. And of course, when you change the materials and you decide to use a stone instead of a conglomerate, the costs will be so high. So this is the final result of the calculation of the difference for each of the 20 streets. And this study has been so useful for the public administration, the Roma municipality, in order to define the new public tenders for using the National Recovery Plan's resources. So effective road design, why this tool is so useful for the public administration? Because streets could really affect the quality of our cities, and could help reducing the pollution, the air pollution, and of course the noise pollution. Will help in decreasing the surface temperature of the streets, and of course reduce the phenomenon of the heat island, and could help, of course, the performance that we have now from the conglomerate are so helpful in order to simplify the water drainage of the streets. Of course, the improvement of the energy efficiency, but in the end, and this is very important for a municipality, improve the point of view of the citizen, also from an aesthetical point of view. So having irregular streets with a high level of maintenance and having the main solution shared, because Rome is so big, and sometimes you just round the corner and have a different sidewalk. So having strict solutions that are shared on the surface of all the city could help the citizen, but also the tourists, to have a nice point of view on a city, pursuing an harmonic management of the maintenance of the intervention. From just few themes that we would like to improve in the next part of the research is to enhance the street mapping that the Roma municipality has already done during this year, according to a GIS approach, in order to be able to monitor constantly the state of maintenance, but also the number of resources that we have already invested on the specific streets, in order to be more transparent and also more effective. So I run very fast, and thank you for your attention.
Thank you. Thank you for the presentation. Now, is there anyone who has questions? We are waiting for your questions, if you have any. No?
There's a question from the. Okay. So there's no question from the floor.
A false alarm. Okay, no fear. Well, okay. We can proceed.
Thank you.
Thank you again. Thank you very much. Now we can go on with the next presentation. The title is "The Usufruct Right as an Effective Strategy for the Enhancement of Properties in the Use." And the presenter, I guess, is Marco Locurcio. Is that right?
Francesco Tajani.
Francesco Tajani. Okay, perfect.
Yes, give me a second.
So you can proceed.
Yes, give me a second. And if you can. Thank you.
Mi sa che alla fine parliamo tutti italiani qui dentro in questa sessione.
Okay.
Sorry for Yasmin. I was saying that I guess we are all Italian in the session, and we all speak Italian here now.
Okay.
Okay. After that, we can proceed. Thank you.
Thank you. Good afternoon. And this presentation concerns a modality of enhancement of public properties. In particular, in the last decades, after in particular the subprime crisis, new alternative modalities of valorization of enhancement.
Sorry, can I ask you a favor? Can you go to the presentation modality of the PowerPoint?
Sorry.
Okay, thank you.
First of all, this and presentation modality. This one, no?
No.
Okay. And do you see?
Just to see the presentation in the entire screen. Not yet.
Not yet, huh?
No? I see the PowerPoint pages.
Now?
No, not yet. But I want to. Okay, I just refreshed my page.
Yes.
So you can proceed, please.
Marco, can you see the presentation?
Well, I see the PowerPoint slide list, not the presentation in the entire screen.
Okay.
But you can proceed anyway.
Okay.
You continue to have problems.
Marco, we check the split in full screen mode. If no, it works. We continue in PowerPoint mode.
Okay, no problem.
FF5, is it the same, no? No, but you see only that. In this way, you see only this. Whereas maybe... You think that
Marco, no?
No.
Okay.
No.
Okay.
I saw you are rolling the slides, but not in the presentation mode.
Now you see in the PowerPoint mode, no?
Yeah, normal mode, yes.
Okay.
No, please don't zoom because it cuts the
Okay.
header and the footnote.
Okay. If you agree, we will live in this way. Okay, Mark?
Oh, yeah, okay, you can go.
I don't know why here there is this.
No problem, don't worry about it.
Okay, so we are talking about different modalities of enhancement of properties. Actually, after the subprime crisis, so in the last decades, we had a new alternative form of investment in the property market, as the reverse charge, the exchange of the property exchange, the rent to buy. Also, for example, the transfer of surface rights as a solution to avoid to purchase a public property for all the risks connected also to the transformation costs and especially for the high market values of these properties. So there is like a modality of concession and lease, we can say, in which a private operator can take the property for some years, 30, 40, 50 years, can renovate it, for example, for senior accommodation, as we will see in this specific case, for a hotel, for a nursing home. And after this period, it will give again the keys to the public administration. These are the direct modality of valorization, the direct modalities. Some indirect modalities are related to the real estate funds, so as a financial instruments. And inside the direct modalities, we have also the bare ownership. So we can imagine to split the full ownership of a property in two components. The bare ownership, that is the related to the bare owner is the person that can transfer the ownership to other people, and the usufructuary is the person, so the person that can use the property, that can exploit the property, and that can, for example, can live inside, if we imagine a residential use, or can also rent the property, lease the property to other people. After the subprime crisis, we saw not only a legal use of these modalities, for example, for succession aims, but also a commercial use, for example, for people that imagine big metropolitan cities in which so young people decide to live alone, but they do not have the possibility to buy a new house. So in this situation, their parents, for example, decide to sell the bare ownership, to live inside the property for all their life. And with the money, with the amount of money obtained through the sale of the bare ownership, they help, they support their sons, their daughters to buy a new house. A different modality to use this mechanism is, for example, as we will present in this case study, for the enhancement of a public property. In particular, in situation in which we have so property asset in disuse, and that can be reused for the satisfaction of community needs of the community. But at the same time, the property is not public, but for example, the owner is another entity. In this case, we will see a religious entity. And there is the problem of a lack of financial resources. So the public entity is not able for this situation to buy the entire property, to obtain the full ownership of the property. So in this situation, we can imagine to find a compromise solution in which the property can be enhanced without the acquisition of the property, but buying only the usufruct. So we have an entity that is the bare owner of the property, then the usufructuary, and the possibility also to have a tenant if we imagine that the usufructuary decides to rent, to lease this property. So about the usufruct right, it's very, we can say, so it's very old. We find it in the Roman legislative framework in Italy, in France, in Spain, and Germany. Actually, is codified through the Article 978 of the Civil Code and subsequent. According to the Civil Code definition, so the right to live, as we said, to use a property, also to rent the property, and the duration is for the life in case of a person, in the case in which the usufructuary is a person, or at maximum 30 years in the case in which we have a legal entity, for example, a company. Constraints: the usufructuary cannot change the intended use of the property. The main costs are related to the custody, the administration, and the ordinary maintenance of the property. So we have this to imagine this, to split these two components: the bare ownership that is related to the possibility to transfer the property, and usufruct right, the possibility to exploit the property, to live inside it, to rent it. So there are different modalities to assess, different procedures to assess the bare ownership value and the usufruct value. In particular, in this situation, we take into account what is provided by by borrowing the logic of the general appraisal, we can say. So it's the value of all the revenues generated, of the actualized the revenues generated by the property, so through an appropriate discount rate, revenues minus all the costs that are burdened by the usufructuary. In particular, in this case, okay, the revenues, for example, related to the rents, and about the discount rate can be estimated to the weighted average cost of capital, in which we have, so the big E and D are the percentage of the equity, so the amount provided by the private, and the percentage related to the debt, for example, for after taking out a loan from a bank, and key D, so the coefficient related, for example, key can be estimated to other methods, as the capital asset pricing method, that take into account in particular the risk premium the reference market and KD related to the debt, not to the part of debt, cost of equity and cost of debt. The case study is located in southern Italy. Is a property to be reused, to be enhanced. The owner is a religious entity, and the public administration is interested in buying only so is interested in taking the property for a specific period. So not to buying not to purchase it, not to buy the full or to obtain the full ownership of the property. So in this situation, the idea is to obtain the usufruct right for a period, in this case, of 20 years, to enhance it, and to rent the property to a third figure. So we have the bare ownership, in this situation, the religious entity, the usufructuary that will be the public administration, the tenant that will be the private that will manage this property for a certain period. So the property, the main building, okay, in general, only some data, gross internal area, 2,700 square meters, with the covered area for the, equal to 900 square meters, and the total area, by considering also the appurtenant area, so the external area, equal to 4,800 square meters. The property, all the property must be renovated. Some photos of the situation, the current situation of the property. So the idea, the refunctionalization for a period of 20 years, and also taking into account, obviously, the highest and best use, so technical constraints, economic, financial and economical constraints, the legal constraints, the highest and best use is a senior accommodation. This also taking into account the current situation, which, for example, in Italy, we have a reduction, as we will hear in this period, of new children, and there is also high presence of old people, also with high life expectancy of people. Also because, as we can see on the right of this figure, we have this situation of a demographic pyramid. So a situation in which we don't have children, and we have a concentration of people, especially around the 45-50 years old. About, in particular, the supply of long-term care beds, so for senior accommodation, we can see that there is also a supply that can be satisfied in Italy compared to the European situation. So this is the project according to the distribution of the all the rooms, all the beds of this senior accommodation, for a total of 64 guests. So total 10 single rooms and 27 double rooms. Okay, so taking into account, generally, the technique that has been used is the discounted cash flow analysis, by taking into account the revenues generated by the rents and all the costs that are burdened by the, in this case, by the lessor, that is the usufructuary, so the administrative cost, the taxes, some vacancies that must be considered. So through a market analysis also about the vacancies, the other competitors, so the tariffs applied by that competitors, the discounted cash flow analysis has been developed. According to this analysis, the value of the usufruct right is equal to 300,000 euro, compared to a full value, so a market value, sorry, the value of the full ownership, equal to 780,000 euro. So there is a convenience because for 20 years, for the use of 20 years, I can, as a public administration, save 480,000 euro because the bare ownership remains in the hands of the religious entity. So we have that the benefit for the owner of the for the bare owner, the fact that they will obtain 300,000 euro and avoids also the maintenance costs. And there is also a saving for the public administration, as we have said, for a period of 20 years equal to 480,000 euros, so equal to 62% of the market value of these properties. So conclusion, this can be a useful modality also for the enhancement of public properties, especially in situations in which we have the lack of public resources, in order to take into account also the needs of the communities and to avoid the high risk correlated, for example, also to a high value that public administration has to pay in the case they decide to purchase the entire property. Okay, thank you for the attention.
Thank you very much. Okay. Any questions from the audience?
Oh, sorry. Okay.
No questions at all? Okay, we are finished. Thank you again. Thank you for your presentation. Luigi, io avevo altre 2 presentazioni in programma, ma non vedo i presentatori, non vedo nessuno dello staff.
Sì, if there are no other people, we can, as you suggest, we can stop the session, because if someone won't join to the session,
I can see anyone who have to present.
Yeah. There's no in prisons. There's no people. There are no people in prison.
Okay, I just try to call.
Yeah.
Next presentation.
The last 2
aerial and terrestrial leader comparisons and accuracies by Gabriele Garnero. Is there anyone who has to present? Gabriele Garnero? No? Next one, experience of using PBL and gamification as an active methodology in time of pandemic in Ecuador. Jose Gomez. I'm afraid we have to reslot these 2 conferences, just 2 presentations. I'm noticing that our time has run out.
Yeah. The last slot was at 10 to 19. Was scheduled. The last slot planned for Jose Gomez.
Yeah, but there is no anyone here. Okay, let's wait 2 or 3 minutes more, and after that we can shut down the session.
Okay.
Maybe the other two presentations are rescheduled.
Probably is a way in the next session tomorrow. Probably if someone wants to reschedule the presentation.
Yeah, I guess so. Anyway, let's wait 2 or 3 minutes more.
Okay.
After that, we can shut down.
Okay.
Okay, that's all, folks. I guess you can shut down. And Damiano told me that you don't have to stop the live streaming because he does it.
Okay. So I shut down from the meeting.
From the room, yes. And after that,
Bye.
ciao Rossana.
Salve.
Thank you, everyone. Good evening.
Good evening. Good evening to you. And after that, I guess you have to report that two presenters are not here now.
Perfect. So, Marco, thank you, and see you soon.
Thank you. See you soon in presence, possibly.
Yeah. You. Marco, have a good evening. Bye.
Bye.